Hello everyone, and welcome to the second video in our Class 8 series of lecture videos, Radical Reactions for Hydrocarbons. Let's consider the chlorination of methane. So here we have methane, diatomic chlorine, and a little light, which we symbolize as H nu, and we're forming methyl chloride or chloromethane. And HCl. So before we consider a reaction mechanism for this above reaction, let's review the thermodynamics of the reaction. The driving force for many reactions is typically enthalpic. So what do I mean? Delta H, and not entropic, delta S, because Gibbs free energy depends on delta H and delta S. The change in Gibbs free energy is equal to delta H minus T delta S. So the enthalpy, or heat of reaction, arises from the difference in the energy released from the bonds formed and the energy consumed for the bonds broken. So let's look very carefully at what our reaction is doing. We're breaking a carbon-hydrogen bond in methane. We're also breaking the chlorine-chlorine bond in diatomic chlorine. So the energy for a carbon-hydrogen bond in methane is 105 kcals per mole, and for chlorine we're at 58 kcals per mole. We are forming the carbon-chlorine bond of chloromethane. That's worth 85 kcals per mole. We're also forming the HCl bond, which is worth 103 kcals per mole. So if we perform this operation, we see that the overall change in enthalpy is minus 25 kcals per mole. But just because a reaction is thermodynamically favored does not necessarily mean it's kinetically favored. So sometimes a reaction needs a little heat, that's symbolized by delta, or light, which we know to be H nu, in order to go. This is the idea of activation energy. In this case, light or heat is needed to start a radical chain. So for example, our diatomic chlorine, it's a gas at room temperature. If it's hit with a photon of the right energy, or if we heat it, we can form a small amount of chlorine radicals. Note, you don't need to homolyze a large concentration of diatomic chlorine for initiation to occur. We only need a few of these forming at any given time to start off the reaction. So what's the first step after we form one or two or a few chlorine radicals? Well, the chlorine radical then goes and bumps into a methane molecule, and in the process it breaks the carbon-hydrogen bond. It abstracts a hydrogen with one of the electrons from that bond, and the other electron in that bond goes to carbon. So we've created HCl, and we've generated a methyl radical. And so the change in enthalpy for this particular mechanistic step in the overall reaction we know to be 2 kcals per mole, because we broke a bond worth 105 kcals per mole and we formed a bond worth only 103 kcals per mole. So the net energy is positive 2 kcals per mole, and this is a propagation step. So organic chemists like to diagram energy versus reaction coordinates for systems. So let's take a look at that. So here we have an energy versus reaction coordinate diagram for that first elementary step in the reaction. We've already initiated our reaction. Light has hit diatomic chlorine. We've generated a chlorine radical, and we have methane gas floating around. That's where we start off. The chlorine radical is going to bump into the methane, and it creates something we call a transition state. So we could, in theory, either proceed to the products of that reaction, or we could fall back to our reactants. If we proceed to the right on the reaction coordinate diagram, we create our products. That is, we form our HCl and our methyl radical. Now the difference in energy levels between our starting reactants and our products is 2 kcals per mole. That's the change in enthalpy. However, the transition state structure is a little higher in energy than our products by about another 2 kcals per mole. So Hammond's postulate and this transition state structure, what's going on at the transition state? Well, it depends on the type of reaction that you have, whether it's endothermic or exothermic. In this particular reaction, what we're seeing the transition state structure more closely approximate is the products. That is, it's more like a methyl radical and HCl, because the bond between the carbon and hydrogen is longer and the bond between the hydrogen and chlorine is smaller. So Hammond's postulate is that for an endothermic reaction, the transition state looks more like the products than the reactants. It typically occurs late. The more endothermic, the later your transition state occurs. Exothermic reactions are the reverse, and we will see this in our next video. How does one think about the transition state? We've kind of gone over this a little bit already. One could think of it as having a structure at the transition state, that double cross position. The reaction could proceed to products or fall back to reactants, and this is the idea of microscopic reversibility. If you're on a journey from one side of a reaction arrow to the other, in theory, your reaction could go backwards at any given point. So we'll go ahead and look at the second mechanistic step and explore Hammond's postulate further for exothermic type elementary steps in the next video.